welcome everybody to this first colloquium of this 2017-2018 several colloquial season. So it's a pleasure to have today as our first lecturer Professor Ichiro Komatsu, Director of the Max Planck Institute of Astrophysics in Garden, and he will tell us about critical tests of theory of the early universe using the cosmic microwave background. Professor Komatsu is also an honorary professor of the Ludwig Maximilian University in Munich, and he has as well several current visiting positions. He is a principal investigator at the Cavalli Institute for Physics and Mathematics of the Universe in Tokyo, and he's a visiting professor at the University of Copenhagen. Professor Komatsu was previously the director of the Texas Cosmology Center at the University of Texas at Austin, and a research fellow at the Princeton University, where he also spent a year during his PhD, carried out in Tohoku University, Japan. So his crucial and extremely well-known contributions to cosmology, in particular to cosmic microwave background studies, with more than 50,000 citations, not 50,000 citations in the literature, has driven the precision cosmology era we are currently living. His leading role in the WMAP satellite collaboration had a deep and highly relevant impact in our understanding of the universe. So, these crucial contributions have been awarded with a large number of very prestigious prizes, and therefore it's absolutely an honor to have Professor Komatsu with us here, and please join me in welcoming him.
Thank you very much. Thanks, Olga, for the invitation. It's a real pleasure to visit Valencia. It's my first time being here. I moved to Munich 5 years ago and being sort of touring around Europe, getting to know people here. So I hope that I have many more chances to come back to Spain in general. And I love Harmony Medical, so I'm really happy. So I'd like to tell you about the current understanding of the early universe that we learned from the cosmic micro background. And a majority of my talk will be focused on what we learned from these little satellites circling around here, but also I'll tell you the latest plus what we're expecting to learn in the future. So I would like to really convince you that the real breakthrough that we had using the CMB research was very simple. With the light that we collect in the microwave, we can, literally speaking, see the physical condition in the early universe. So all you have to do is to collect this light from the early universe and try to understand how the universe works. And for example, so the universe was born, it's expanding, it's hot and dense, and you can't see anything through because electrons and photons are still interacting each other through Thomson scattering. So not until the universe temperature went down to 3,000 kelvins that we finally have the transparent universe, just like this. So that's 3,000 kelvins, 380,000 years after the beginning of the universe. Now we can see through the universe. Now, the very important thing to my talk is that you saw already the existence of irregularities, existence of ripples in the temperature, right? So you see now these clumps. And according to the standard model of the cosmology, small things emerge first, then these little clumps merge to form bigger and bigger and bigger structures. But if we didn't have such initial irregularities well before first galaxy was formed, these things wouldn't even exist. So the big question is, first of all, we see these initial ripples in the sky. But then, what created them is the next question. And that will be the main topic of my presentation today. So these things, in the meantime, continue to merge together, and they eventually form a Milky Way. And Milky Way will eventually collide with Andromeda Galaxy and form something else. So this is the hierarchical structure formation in the universe, and we seem to understand the evolution of these structures pretty well. Yeah, you see? Yeah. have a Milky Way and Andromeda, and they will collide eventually. Okay, so if you look at the night sky in optical, this is what you see. But then, let's say Apple, who just announced the iPhone 10, but eventually they might announce Apple glasses that might be sensitive to microwaves, and if you wear them and look at the sky, doesn't matter if it's day or night, then you probably see something like this. So this can be said to be the actual real image of the cosmic microwave background in the sky, and this light from the fireball universe filling our entire sky. It's no longer 3,000 kelvins, it's 3 kelvins, because the universe has expanded factor of 1,000 since the universe became transparent. This is CMB, and if you count, now I told you that we can collect these photons using the microwave telescopes. If you count number of photons per cubic centimeter, it's 410 photons per cubic centimeter. And this is the most numerous particles in the universe. Of course, locally on Earth, we have many more particles than photons, but if you go to the average space, you count number of atoms, you count number of photons, you compare, then you realize that there are, let's see, 2 billion, so 1.7 billion photons per atom. So this is by far the most numerous particles in the universe. And the second most numerous is neutrinos. Okay? All right, so you can use your microwave dish telescope to do it, or, so this is Professor here in Paris, she was also a member of the WMAP collaboration, and she's holding this TV, well, so these things probably don't exist anymore, but if you remember what this was, you tune your TV channel to something that doesn't transmit the TV program, then you see just static noise, and 1% of that noise is actually due to CMB. So it doesn't really take rocket science to detect these things. These are numerous. So back in 1965, these two gentlemen here used this big antenna in Bell Lab, New Jersey, to look for something. So these were PhD in astrophysics, and they wanted to measure the brightness of supernova remnant called Cassiopeia A. And this thing moves, fully functional, right? So I took this video at the Deutsche Museum in Munich. This is 1 to 25th model of the antenna. This is fully functional, so you can look at any location in the sky. Okay? Big. So this is the real recording system that was used by Penzias and Wilson to discover cosmic microwave background. And Penzias was born in Munich, although his family had to flee to US because of this emergence of Nazism in Germany. He kindly donated this his instrument to Deutsche Museum. I was crying right when I saw this. I don't know if you can see it, but this is me in reflection. I'm taking a picture. Right, so light comes in, and then goes through this horn antenna, or horn, and then goes here, and it's amplified because the light from the sky is too weak. Then it's sent to the recorder. So this is really just the same thing as a radio that you are very familiar with. It gets the signal from the radio station, amplifies, and you can hear it. But difference between radio and this thing, which is much more expensive, is the existence of the calibrator here. Okay? This is the liquid helium cooled down to 5 Kelvin. And why do you need this? Because so you look at, what you're trying to do is to measure the brightness of the sky in absolute term. But if you just collect something from the sky, you measure things in voltage, for example, you don't know what that temperature corresponds to. So you need to basically switch between sky as an input or the calibrator as an input and go back and forth. And then you measure, then you can calibrate what you see in the sky. So this is a major difference between radio that you know and this system. And Penzias designed and built this, and this was crucial to the discovery of the CMB. Now, this is fascinating, okay? So as soon as they turned on their instrument on May 20th, they immediately knew that something was wrong. Okay? It didn't take them more than 20 minutes or something to realize that there was a real problem. What is this? This is a recording. As we go to the right, it's higher voltage or higher temperature. Go to the left, it's lower, and time flows from the bottom to up. And here, you can't see it, but it says cold something. So this is calibrator. So reading of the calibrator is this. Elevation 90 degrees is zenith. And you can see that zenith is brighter than the cold 5 Kelvin. Right? But it shouldn't be. Because sky at 7 centimeters they're observing is only 2.3 Kelvin. And so 6.7 Kelvin is what they recorded in the sky. You subtract 2.3 Kelvin, that's coming from the atmosphere. Now, antenna itself emits some small signal, that's 0.8 Kelvin, and everything else is 0.1 Kelvin or below that they quantified. Now you do the subtraction, and you're left with 3.5 Kelvin. Now you see that jitter here, right? The noise in the recording is tiny compared to the signal you're looking at. So this is a very, very high signal to noise, precise measurement. Statistical uncertainty is completely negligible. Where does this plus minus 1 come from? This comes from your knowledge of the sky temperature. So 6.7 here has 0 error, basically. But the 2.7, the 3, atmospheric temperature has some error. The antenna temperature has some error. Everything else also has some error. So you add them up in quadrature, you come up with 1.0 Kelvin. So in other words, 3.5 detection is many sigma. But compared to systematic uncertainty, it's something like 3.5 sigma. Okay? But that's significant. Alright, so that was a discovery. And then that turns out to be the signal from the Big Bang. But if you just measure a thing at 7 centimeters, something like here, for example, then you won't know whether this is actually the stuff coming from the firewall universe, because you have to show that the data points should fit a black body spectrum. So this is a black body spectrum of the not 2 Kelvin that's here, not 4 Kelvin that's there, but it's 2.725 Kelvin. Okay? So with this, you know that somehow cosmic macro background is in thermal equilibrium, but we know that today we exist, therefore universe can't possibly be in thermal equilibrium, otherwise we wouldn't exist. So what this means is that the universe in the past was in thermal equilibrium. So that's the proof that the universe was once fireable. Okay, now, moving forward, 2001, we launched this couple of pairs of dishes. We went to L2, so this is the team. Chuck Bennett is the PI. And, so we observed the sky for 9 years. So, let's look at the sky in multiple wavelengths. So what you're going to see now is the sky in different wavelengths going from the optical to longer wavelength. So you go from optical, near infrared, far infrared, sub-millimeter, and microwave. And this is how we project something on the sky, right? So this is galactic plane. And so near infrared, far infrared, sub-millimeter. You see galaxy, but by the time you go to microwave, it's CMB. Everywhere you look, it's approximately 2.7 Kelvin. But if you look deep enough, if you improve your sensitivity of the instrument by a factor of 100,000, you see these ripples, fluctuations. Except this galactic plane, these are the real ripples that existed when the universe became transparent 380,000 years after the beginning of the universe. Yeah? So with this, we can learn something about the universe. Now, let me explain this telescope first. So we have 2 antennas. Why? So imagine that you do this Penn-Wilson experiment. Okay? So you have telescope, you have calibrator, you look at the one location in the sky, you switch back and forth between sky and calibrator and measure the temperature. 5 minutes later, you do the same experiment, but looking at a different location in the sky. You record something else. and you compare. If they are different, you conclude that sky has fluctuations. But wait a minute, right? Calibrator temperature might have changed. It does change, okay? And ground pickup, namely you look at the sky, okay? There's a ground also emits something. Maybe there's a leakage from the ground to the telescope. Or maybe telescope's temperature also changed, and emission from the antenna also changed. We're talking about 30 microkelvin, no longer 3 Kelvin. So to be super careful. Right? How do you make sure that the variations you see in the sky is actually real and not something coming from in the instrument? The answer is you do differential measurements. You have 2 telescopes looking at different locations in the sky. You receive light, at the same time you differentiate. So any changes in the instrument will cancel out to large extent, and then what you see in the sky will show up in your recording. It worked very well, and that's the image we have. And let's see. Now if you look at, so what we think now, this is the distribution of photons. And, but now we can map this distribution of photons into distribution of matter using some cosmological assumptions. And what we think now is that this is where we all came from. Okay? So this is eventually the overdense region will form stars, will form galaxies, will form planets, will form life. So with this WMAP satellite, and COBE satellite that detected the isotope for the first time in 1992, we think we nailed our origin. Okay? So that's pretty cool. So what WMAP taught us, galaxies, stars, planets, and ourselves ultimately originated from tiny fluctuation in our universe. So that's the fact. Now, let's try to understand this better. Now, I have to apologize if you don't know what this is. So this is a Japanese soup, national soup called miso soup. Miso is the bean, soybean, and we create soup out of that. This white thing is called tofu, that's also made of soybean. So when I give this talk in different countries, I try to use soup in respective countries, but it's very hard to find something that's not very sticky. So when I was driving with young folks yesterday from Teruel to Valencia, I was asking them for suggestions, and they gave me very good suggestions, gazpacho. And I thought that was a very good idea at that time. When I thought about this a little bit after when I was in hotel. Gazpacho is too sticky actually, so it actually doesn't work for the thing that I'm going to tell you now. And I got another suggestion. What about the orange juice? Well, that's pretty good too, but I wanted to stick to the soup. So, well, anyway, so this is the cosmic miso soup, okay? And when matter was ionized, when the universe was hotter than 3,000 kelvins, it really acts like a sauce, so it acts like a soup. It's plasma, and when you drop tofu into the soup, it creates ripples. So now you know the problem, right? If you drop tomato into gazpacho, it doesn't do anything. So you really have to have ripples created. But then, because miso is also a bit sticky, this waves damp. There's a viscosity inside. And this is exactly what we measure in the cosmic micro background. It's ripples created by something that damps. And if you change the density of the miso, for example, damping changes, or the sound speed changes, and many things change. So not just one tofu, but now we drop many, many tofus, then it creates ripples everywhere, and then maybe that's what we see in our sky. But to really, I mean, the real space picture is a bit complicated to analyze. So why don't we go to Fourier space? So what we do is to take the data, decompose temperature fluctuation in the sky, in a series of sine, cosines, Fourier transform. Because we're reading with a sphere, we actually do spherical harmonic transform, but it doesn't matter, it's the same thing. Then we make a diagram showing the amplitude of waves as a function of the wavelength of the waves. In fact, x-axis is inverse of the wavelength, so it's wave number. And we see this. So the y-axis is the amplitude of waves, x-axis is the 1 over wavelength, and you see this damped cosine oscillation. And if you change the ingredients of the soup, waveforms change, and by which we can measure compression of the universe. So, if you look at this leftmost thing, this is the longest wavelength. Longest wavelength is basically the wavelength that's comparable to the size of the sky. Then as you go to the right, you start seeing the shorter wavelength. Yeah? And then you keep going, and then you see this shortest wavelength you can resolve by the instrument. But then once you combine them together, of course you get what you started with. Okay? So this is the power spectrum. And if you change the amount of meso, or amount of atoms, first peak increases, second peak decreases, third peak doesn't change, and so forth. Now you change, so this is the change in the power spectrum due to the change in the matter that interacts with photons. So this is the consequence of really of the meso soup. Okay? But you also have matter, and due to general relativistic effects, they change temperature of the photons by gravitational redshifts and blue shifts, by which you can now measure the matter that may not interact with photons. So this is the effect of the total matter, and if you decrease the total matter, first peak goes up, second peak goes up, third peak goes up, right? So this is very distinct compared to the effect of something that interacts with photons. So in this way, you get the full account of matter. You know the abundance of matter that interacts with photons, and the abundance of matter that doesn't interact with photons. And you hope that, so this total matter and baryons agree, but they don't. So it turns out that in the present day universe, 5% is atoms and 23% is dark matter, something that doesn't interact with photons. But then, if you add them up, they don't even add up to 100%. So rest is not matter. That's why we call this dark energy. Why do we know it's not matter? Because if it were matter, it should show up here, and it didn't, right? So everything else is now something that's not matter, something that doesn't clump. All right, but that's not what. Okay, that's a cool thing. But the question I want to ask today is who dropped togus? Because you see that if somebody dropped togus into the soup, something happens, right? Ripples created and damp. But you really need someone dropping togus in the first place. If no one dropped the togus, nothing happens. Right? The soup stays still, and you enjoy soup. Who dropped togus? It turns out that no one dropped togus. This is the togus that quantum mechanically emerged from the vacuum. So this is tohu quantico. Right? It's quantum tohu. That's pretty remarkable, right? So this is basically quantum mechanics at work in the early universe. Let's look at uncertainty principle, and I know that this is not really correct statement, but believe me, we do proper field theory calculations and so forth. But just for the sake of pedagogical explanation, let me say, energy you can borrow is inversely proportional to the time you borrow. So if you promise to return, immediately you can borrow a large amount of energy out of the vacuum. So you go to the bank, you ask for €1 for 10 minutes, and they would probably lend you €1 for 10 minutes. Okay? So they think you're crazy, but they may lend you. But if you ask €1 million for 10 minutes, then they would call a police. But if you promise to return 1 million euros in 0.1 seconds, and they may lend you and you just give it back, right? They may call you an ambulance, but because they think you're crazy, but not police, but that's okay. So the thing is that time was very short in the early universe. So you have a lot of energy that you could, in principle, borrow. That's okay. And then maybe this is the origin of our galaxies. But wait a minute. Of course, in this room, there are quantum fluctuations. But they never create galaxies. But they stay on the microscopic scales. What's the missing link? What's the missing link that connects small-scale world and large-scale world? That's cosmic inflation. So these folks postulated that maybe in the early universe, there was a rapid exponential expansion that stretched wavelength of the quantum fluctuation to macroscopic scales. Quantitatively, what you need is something like in 10 to the minus 36 second, wavelength has to be stretched by factor of 10 to the 26. In other words, something like the size of atomic nucleus would become the size of the solar system in 10 to the minus 36 seconds. This is crazy. This is totally crazy, right? So you're sitting in your office, undergraduate student knocks on your door and say, Professor, I think I know where we came from. It's quantum fluctuation. And the space was stretched by factor of 10 to the 26 times in the 10 to the minus 36 second. And what's your reaction to that? You'll be like, what? Just read random Lifshitz once again and come back, right? That will be your reaction. So that's cosmology. Okay? Cosmology is fun because something that looks utterly crazy may be true. And everything we observed so far agrees with this prediction. And I'll try to convince you of that. So basically inflation is a magnifier. And in this bank example, right? So they lend you 1 million euro, and you promise to return it in 0.1 second. But in that 0.1 second, distance between you and bank was stretched exponentially, and you are now even out of the causal contact. So you don't even have to return the money. That's inflation, you see? There you go. So inflation creates quantum mechanically two things. One is gravitational potential, which we call scalar mode, that's theta. And another thing is gravitational waves. Now what's the distinction? So we measure distances between 2 points. This is the distances between 2 points. And this is the Pythagorean, Euclid thing. X squared plus y squared plus z squared is distance square. But then due to this, first of all, due to the expansion of the universe, you have the scale factor multiplying the distances. So as time goes on, A increases, that's the expansion of the universe. But then due to fluctuations, distances between 2 points increases isotropically. Or decreases isotropically. That's gravitational potential, theta. But you can also have anisotropic stretching between 2 points in space while preserving the area. So determinant is 0. That's a condition for that. So that's gravitational waves. And so we want to measure both. And the basic point here is that energy you can borrow is inversely proportional to the time you borrow. Now, so let's define the expansion rate of the universe. That will be A dot divided by A. This has a unit of 1 over time. Therefore, energy you can borrow should be proportional to h. And that's exactly what happens. Both zeta and hij are proportional to h. And because inflation happens so short amount of period of time, this h in natural units corresponds to 10 to the 14 GeV. Right? That's why we're excited about this possibility. This is the one way to probe such an ultra high energy universe. And important thing now is that so inflation continuously produces fluctuations. Okay? So time 1, fluctuations are produced and the wavelength is stretched. That fluctuation is proportional to the h at that time. Somewhat later time number 2, fluctuations are produced and stretched. And because the timer number 1 was earlier, it had more time to be stretched. So this fluctuation produced earlier appears as a longer wavelength fluctuation in the sky, let's say 10 degrees. The fluctuation produced later would then subtend 5 degrees, or 2 degrees, or 1 degree, and so forth. Okay? So this is, using this fact, you can map values of h as a function of time. Because the inflation has to end, h should decrease. Okay? Therefore, quite generically, not always, you can always find exceptions, but quite generically, inflation predicts that the amplitude of fluctuation on large scales is slightly bigger than the amplitude of fluctuations on small scales. Okay? That's what we want to find. That's one way to say that inflation actually occurred. But if you look at this power spectrum, it goes up, down, up, down, up, down, right? So it doesn't look like large scale is bigger than the small scales, or whatever. But we know that this is what sort of artifacts, if you like, created by interaction between tofu and miso, right? So but now that we measure the amount of baryon, the amount of dark matter, amount of dark energy in the universe, we can redo, or we can get rid of oscillations, and we are left with something that looks like this. So in this case, this is precisely scaling variant, namely the amplitude of fluctuations is equal at all angular scales. But inflation could have done this, or could have done that. So let's parameterize the slope by ns. So if ns was 1, it would be precisely scaling variant. If ns was less than 1, it would look like this. So with doubling up nonlinear data only, we could find that ns is indeed less than 1, but only 2 point something sigma, 2.2 sigma. So that's a hint, but not decisive. Now you can, although in space you can launch something like 1.5 meter diameter dish, so this is 1.5 meter diameter dish. You can't fly 6 meter dish. Well, JWST is like 6 meter, but it will be very expensive. So what you can do instead is to build telescopes on the ground. This is Atacama Cosmological Telescope in Chile, led by Princeton, and this is South Pole Telescope in South Pole, led by Chicago, University of Chicago. And you can, with this, you can have a bigger lever arm, so that you can determine slope better. Now we have 3.5 sigma evidence, but not decisive. Now you can also, so at that time, W9-year release, combining this, we could find 3.5 sigma. And if we now use galaxies, distribution of galaxies instead of CMB, we could find out of 5 sigma discovery of ns less than 1. But this is like, right? So what is this about? This is like, so your kids ask you, Mom, where did I come from? And you say, yeah, right? But then you say, well, they say, so where did you come from? And you say, I came from your grandmother and grandmother. And then they keep asking, where does that come from? And you say, Earth. Where did Earth come from? Protoplanetary disk around the sun, so it's sun. It came from the sun. Where did the sun come from? Blah, blah, blah. It's galaxy. Then kids ask, where did the galaxy come from? And of course, in college, you don't learn that, right? Anything beyond galaxy is just out of your imagination. So you tell kids, go to bed. None of your business. But now we can tell kids, perhaps, it came from quantum fluctuations in the early universe. But are we ready to say that? Okay? To say that, you really want to have something robust. No, you don't really want to combine CMB on one hand and galaxies on the other hand. It's much better to do it all at once from the CMB only. So this is a successor of WMAP launched by ESA. I'm not involved in this study, but they produced these beautiful results 2 months after our, 3 to 4 months after our final results. And then they used our data and their own data to conclude that NS is less than 1, more than 5 sigma using CMB data alone for the first time. This is a milestone. This is really amazing, okay? And now we are one step closer to saying kids came from quantum fluctuations. Now, this is one way. This is great. This is using the Heisenberg's uncertainty principle. So certainly we qualify to say we found evidence for the quantum mechanical origin of fluctuations. But we want to do something better. We need confirmation. So let's go beyond power spectrum. The quantum fluctuations on the ground state in the vacuum obey Gaussian statistics. Okay, you solve Schrödinger's equation on the ground state in the vacuum, then wave function is Gaussian. So this is Gaussian. So this is a histogram of the temperature values. The histogram of, yeah, that's right. So x-axis is the temperature fluctuations in units of number of sigmas. So 2 sigma, 3 sigma, 4 sigma. And the y-axis is the number of pixels, normalized somehow. This is the prediction of Gaussian fluctuation. This is the data. Right? So it's amazingly Gaussian. Now we can do better. We can do quantitatively better by measuring so-called 3-point function. So because Gaussian is symmetric, if you multiply this histogram by temperature fluctuation cubed and average, you get 0 to within the experimental uncertainty. Or you can do even better. It's somewhat more time consuming, but you can multiply temperature values at 3 different locations in the sky and average. This is a more stringent test of Gaussianity. And what we can say is, with WMAP, we couldn't find any evidence for non-Gaussianity. We could limit that. For example, you can write down your curvature perturbation potential as the sum of Gaussian square with free amplitude, and we didn't find any evidence for non-zero value of FNL. And because this zeta is 10 to the minus 5, small. So the second term is smaller than the first term by 10 to the minus 5 times FNL, or times 3 or 5. So at the 2 sigma level, you can say that the second term is smaller than the first term by 0.2% at the most, at 2 sigma. And the Planck improved our limit by a factor of 10, and now we can say non-Gaussianity should be smaller than 0.03%. And this is, I don't know about you, but this is like a most precise Gaussian function I've ever seen in my life in nature. And I've seen Gaussian thing in noise, but not in a cosmic signal like this. So this is quite remarkable. Now, are we ready to say inflation happened and we all came from quantum fluctuations? Maybe not quite yet. Maybe yes, but maybe not quite. We haven't found primordial gravitational waves. Okay, so extraordinary claims require extraordinary evidence. The Carl Sagan puts it very beautifully. The same quantum fluctuations could also generate gravitational waves, and the gravitational waves, stretch space anisotropically. Now, let me first tell you something. Gravitational waves. Okay. So we've all heard about gravitational waves detected by LIGO, exciting, opening up the new avenue in astrophysics and so forth. These gravitational waves has the wavelength of billion light years, right? So ultra wavelength gravitational waves. If you find it, there's no question that there was this remarkable expansion of space in the early universe. That's why we want to find this. All right, so how do you measure this? How LIGO works is that you have these 2 mirrors here. You have a beam splitter, and you shift the phase of the light for this and that, so that when light comes back and recombined, there is no signal. So troughs of and crests of light waves cancel. But when gravitational waves propagate, it stretches the space in vertical direction. Signals no longer cancel. That signal is no longer cancelled. So that's how you declare that you've seen something like gravitational waves. But you can't do this for the signal that has a wavelength billions of light years. So how do you measure this thing? So we use universe as a detector. Let's say you have isotropic electromagnetic fields like CMB. Gravitational waves propagate, and because space gets stretched, right, like that, wavelength of the light also gets stretched. If the wavelength of the light gets longer, with redshift, so the temperature drops. Right? So you see cold spot here, and you see hot spot from the point of view of somebody lives up there like electrons. So these gravitational waves propagate, and then they automatically generate temperature anisotropies. But more importantly, when this hot, cold is scattered by electron here and coming toward you. Now imagine that you have this plasma there, literally here, and you are receiving light, your observer, seeing the light coming from this particular electron. Right? Then this light is polarized. And why? Well, for example, when you have the windshield of the car, sunlight hits and coming toward you, and it's horizontally polarized. When you have this incident light coming from one particular direction, the scattering or reflection will generate polarization. How do we know that? Because if you, let's say, ask Talex, which makes polarized sunglasses, then you order sunglasses that will block light that's horizontally polarized and it transmits light that's vertically polarized, and you can see through the car. Right? Now let's go back, because the universe doesn't have preferred direction, like this one, right? But what it does have is this quadrupolar anisotropy. So here, clearly, this direction has hotter than that direction, and this is sufficient to create polarization. Right? What's more, because gravitational waves have these two distinct modes, right? This and that. And of course, this is called plus mode, this is called cross mode. Of course, what is cross? What is, what did I say? So this is plus mode, this is cross mode. And what's plus, what's cross? Depends upon your coordinates. You tilt your head by 45 degrees, and plus goes to cross goes to plus. But the fact that they coexist is coordinate independent statement. So here, statement is, when you see one polarization direction, there must be accompanying 45-degree tilted polarization. That's the prediction. All right. So let's see. All right. So let's say, so this polarization hasn't been found yet. Okay? We were working very hard on finding it. But what if it's found? Okay? Then what's the next step? So once it's found, I think nobody doubts that inflation happened. So that will be triumph. But then not only that, but now we can start learning about inflation. So let's define this amplitude of the gravitational wave divided by amplitude of gravitational potential, what we call tensor-to-scalar ratio, tensor fluctuation, scalar fluctuation. Current upper bound is 0.07. So we haven't found non-zero value. So if you plot tensor-to-scalar ratio versus this ns thing here, so ns is less than 1, we haven't found positive r, therefore contour doesn't close. But what we can say is that the specific inflation model makes specific prediction for combination of r and ns. So in this phase diagram, you can now rule out this model, and you're no longer allowed to talk about this thing. And that's kind of, I was shocked. So when we ruled out this model back in 2007, I was shocked because my supervisor in Japan always said this is the most natural model of inflation. And many people agreed. But then once we ruled it out, I start hearing theories saying this is the most unnatural model of inflation. Right? Because lambda was 10 minus 12 and so forth, blah, blah, okay, that's fine, whatever. But then, this x squared phi squared was the next most natural model of inflation. And that's again ruled out once you combine, this latest thing. So, at this point, we have no idea. Just keep going, and this r squared inflation happens to be the prediction from the very first model of inflation that was proposed by Alexei Stravinsky in Moscow. So maybe that's the next target. Well, somebody claimed that they have found it. So they say this, there was a press release in March 17th, 2014. Harvard, Minnesota, and Stanford people said they found evidence from 45-degree tilted polarization pattern and made a splash, blah, 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 even Germans picked up on it. But then, January 30th, it turns out that this was created by polarized light from the thermal dust particles in Milky Way. So, okay, this happens. So current situation is we haven't really found anything yet, so we want to do more in the future. And now JAXA, well, Japan didn't really play a big role in CMB research before, but now United States and Europe turned down the proposals for doing polarization dedicated CMB satellites, but JAXA down-selected this mission. So we are hoping to launch this thing in 2025, 2026. It's selected in full next year. Target sensitivity is something like factor of 100 better than today. And so this satellite has a few thousand superconducting detectors in space, 15 bands, so that we can remove dust polarization well. And we are one of the two competing missions. So we're not selected in full, we're still competing. And then a final selection will happen sometime late next year. So I hope that they will be selected. Okay, so conclusion. With temperature fluctuations, without polarization, I think we already found pretty strong evidence for quantum mechanical origin of our structures. NS and Gaussianity. FNN. But next goal, because to convince the world, well, ourselves also, that we all came from quantum fluctuations through inflation, we want to find unambiguous measurement of polarization from gravitational waves with the billion light year wavelength. To do that, we have a lightweight proposal. I forgot to mention one important thing, by the way. So we don't really need satellite to discover this thing in principle. Discovery may come tomorrow. There are lots of ground-based and balloon experiments doing exactly the same thing. So our hope, at least my personal hope, is that they get there first. And then with the LightBird, we have a definitive measurement of the spectrum of gravitational waves. Then we can do further stringent tests of quantum nature of these gravitational waves. For example, we can do Gaussianity test of gravitational waves too. I emphasize that if we just measure gravitational waves in power spectrum, well, that's pretty good, but we shouldn't forget to do what we did for temperature, namely to test Gaussian distribution of detected gravitational waves. If it's not Gaussian, then in fact that will be telling us that it may not come from quantum fluctuation. It may come from something else. Then we can still learn a lot of the inflation, so I'm excited about the possibility. Well, so that's our goal over the next 10 to 15 years. I stop here. Thank you very much.
Thank you very much, Ichiro. Questions for Ichiro?
Yes, something. Okay, thank you. So thank you, Ichiro. This is a nice story, and also here we have a story for kids. It's just trying to teach them how social life. That is called the Gruffalo. And then you teach things, series or stories, but you have to invent the Gruffalos. In this story that you were telling us, you also have several Gruffalos. So you have dark matter, you have dark energy, you have inflation.
Right.
If we don't understand what are these Gruffalos, how do you characterize this story as real, as verified? So how important is verifying who are these Gruffalos?
So we don't have to understand dark energy, dark matter to learn about inflation, because what dark matter, dark energy do is to create this thing here. But what we're interested in is what's left after removing them. And to remove this thing, we don't have to know dark matter except that they cause gravitational redshift and blue shift, and they don't interact with photons. That's all we care. So I think this thing is very robust against the nature of dark matter, nature of dark energy. Inflation, right? Of course, that's what we're trying to prove or verify. So we don't really know how inflation happened, but the working definition of inflation is that there was an accelerated period of expansion in the early time, so that wavelength gets stretched. So that's the only definition we need. Right? And then we can draw some predictions from them, like ns less than 1, which we can use to verify inflation. That's exactly what we're doing. So ns less than 1, no non-Gaussianity. So we checked two things here. If we want, we verified a couple of other things. For example, existence of this very long wavelength perturbations, which appears to be non-causal, because there's such a large long fluctuation. So this so-called super-Poisson fluctuations, we verified that. Checked. And then something called adiabatic fluctuations that I don't want to get into details on. So we have 4 things checked: super-Poisson fluctuation, adiabatic fluctuation, Gaussian fluctuation, and SSM1. Right? But we have one last thing. That's the existence of primordial gravitational waves. Once we did that, then I think that's quite strong evidence for inflation. So yeah, we want to tell stories, but we were pretty confident already, right? 4 out of 5 is checked. But we want to be really sure before we really tell kids real stories.
Thank you. So more questions? More questions for Ichiro?
I like to speak loudly. So, can you measure the 4-point function of
Yes.
the temperature? And
Yes.
does it work that you get like product 2-point function?
Yes. Oh well. Yes. So that's the Gaussian term.
Yes.
But once we subtract Gaussian square piece, there's
Yes.
nothing left.
Okay.
Yeah. Thank you for asking. Yes. We've done that. Yes.
More questions?
So how? I don't know why it's working. It's working and then suddenly it's not.
Okay, so when you mentioned that you
Expect that the current ground telescopes
Yeah.
this gravitational primordial gravitational wave signal. What are you thinking of? ACT?
Advanced ACT, SPT, 3G, and then polar bear. Okay, so ACT in Chile, polar bear in Chile, that will soon become Simon's array in Chile, class in Chile, and then ACT and polar bear, Simon's array, join the force together to create Simon's observatory in Chile. In South Pole, we have South Pole telescope, and then bicep Keck array experiments. Then we have balloon, so spider, balloon that flew, Piper that's yet to be flown. So we have lots of. And then in Europe, Spanish experiment called Quixote in Tenerife. And then we have Italian, Spanish experiment called LSP. That's combination of ground-based and balloon. So we have lots of modes. And I really hope that, so the next target is R, Tensor-to-scalar Ratio of 0.01. And I think, frankly, there's a good chance that something will be measured at that level. And if not, of course, we have to wait until light bird. But if we see it there, because light bird sensitivity is 10 times better than that, we can really have a beautiful characterization of the signal we measure. So we can do real science with it, not just detection. Detection would be great, but we want to learn a lot of the inflection, and for that we need to have a lot of signal to noise. So that's why.
So,
How much does it cost?
I was that right?
Yes.
So JAXA's cost cap is $300 million. So it's not much, including launching cost, but excluding labor, because Japanese way of accounting things doesn't include salary. But then NASA has a mission.
They don't get salary.
Right. So NASA's mission of opportunity. So NASA, we have an American participation, and the hope is that they use mission of opportunity of NASA to contribute something like $60 million. Now we're also working in Europe to form European participation to LIGHTBIRD. I don't know exactly how much, but something similar order like NASA participation may be possible. I don't know. ESA's mission of opportunity. So that's the kind of ballpark. So it's not going to be $1 billion experiment. It's fairly modest, I must say, compared to some of the other bigger missions.
Thank you. I wanted just to go to your question about the buffaloes or dragons or whatever you like to know. And in particular, I think that there is something important in the connection between the large-scale structure and the cosmological radiation,
Yes.
which is the baryonic acoustic oscillation.
Yes.
In my point of view, this is a point where, for instance, dark matter can win a lot of credibility, because in both things you have seen Saharan peaks, and this is also found in a completely different cosmological probe, that is the early universe mapped by the galaxy distribution. And this is quite different of other evidences of dark matter, for instance, in clusters of galaxies, of the rotational curves, of the velocities in the spiral galaxies. The fact that this simple idea of the acoustic oscillations due to baryonic matter, that fits quite well in both things. I think that it's really a good point supporting this idea.
Sure. I agree, yes.
If there are no more questions for Ichiro, let's thank him again. Ichiro will be here also tomorrow, so we'll be around, so you are interested in talking to him.